Greetings and welcome to Physical Science at Hack. The purpose of this video is to walk through a couple of the example problems from Chapter 8 on periodic properties of the elements. So this will begin our unit on chemistry, and we'll walk through a few of those problems as we did with the physics section that we have just finished. So the first problem asks us to determine how much energy is needed to move an electron in a hydrogen atom from the second energy level into the sixth energy level, and you're asked to give it in two different values. You're asked to give it in joules and in electron volts, two different ways of measuring the energy. So we have to find first of what those energies are. So let's find that the energy at the n equals 2 state is equal to, and you can get these as I note there in figure 8-11 will give you the values that you need. The energy of the n equals 2 state is negative 5.44 times 10 to the minus 19th joules. Or it's also equal to, in electron volts, that would be negative 3.40 electron volts. Now we need both of them. We'll also need the energy for the n equals 6 state, and that is again given in the same table, and that would be negative 6.05 times 10 to the negative 20th joules, or negative 0.377 electron volts. So now we have the numbers that we need, and we just need the difference for these two, for the two values that we're looking for. So let's look at part A here. A, we need to look at it in joules, so that would mean we'd need the energy from n equals 6 minus the energy from the n equals 2 state. So we just have to subtract those two to get the energy difference. And n equals 6, that was negative 6.05 times 10 to the negative 20th minus a negative 5.94 times 10 to the negative 19th joules, which equals, if we subtract those two, we will get positive 4.84 times 10 to the negative 19th joules. And that is three significant figures, which is correct. We should get that same answer for that. It should be in three significant figures, as both of our input numbers were in three significant figures. So that's part A. Now for part B, we need to do the same thing, but in the electron volts. So we're still going to subtract the n equals 6 minus the n equals 2, and we will then find in this case it is equal to negative 0.377 electron volts minus a negative 3.40 electron volts. So same thing, just a different unit for the energy. And if we subtract those two, we will find that that is equal to a positive 3.02 electron volts. So those would be our two answers here we'd see. This would be the answer here in joules, and this would be the answer in electron volts. Both are going to be in three significant figures because both of the numbers that went into them had three significant figures. So that's our first problem. Our second problem, in this case, tells us about some of the measurements that were done. And Thomson measured the charge to mass ratio of an electron and found it to be negative 1.76 times 10 to the 11th coulombs per kilogram. So he knew those two, but he didn't know either the charge or the mass. So we couldn't determine all of the numbers we wanted to. Millikan was able to determine the charge on the electron and found that that is 1.60 times 10 to the negative 19th coulombs. So What do we know here? Let's write up what we know. The charge of the electron equals negative 1.60 times 10 to the negative 19th coulombs. We also know that the charge to mass ratio, so the charge of the electron divided by the mass of the electron, is equal to negative 1.76 times 10 to the 11th coulombs per kilogram. So we know those two. Since we know those two, we can now go ahead and find out what, now that we know what the charge is, we can plug the charge in here in the equation. So we can take the charge from here, put it into this ratio that was found, and then determine the mass. So if we did that, we would get that negative 1.60 times 10 to the negative 19th coulombs divided by the mass of the electron is equal to negative 1.76 times 10 to the 11th coulombs per kilogram. Now we want to solve this for the electron, so essentially we can multiply both sides by the mass of the electron, divide both sides by this value, and in essence what that does is that gives us negative 1.60 times 10 to the minus 19th coulombs divided by negative 1.76 times 10 to the 11th coulombs per kilogram is equal to the mass of the electron. Or mass of the electron is now equal to, and if we divide those two, we'd get 9.09 times 10 to the minus 31st kilograms. Three significant figures, correct, because we only had three significant figures going into that. So that would just be three significant figures, and that would be our answer. Now we can actually determine the mass of the electron. Now those are our only two that are actually calculation problems here. We'll see that with our chemistry side that a lot less is actually calculations. So let's go on to the third problem here. Third problem tells you to refer to figure 816 in your textbook and to write the electron configurations for these three atoms. So we want to write the complete electron configuration. If you recall that, if you take a look at that figure, that's the one with that big zigzag, which tells you which levels fill at a time. So let's look at the first one. The first one is the element argon. Argon, we have to look up how many electrons does argon have. Argon has 18 electrons. So we want to work our way through until we fill up 18 electrons. So as we work our way through that chart, we see that the first thing that fills is the 1s level, and that has 2 electrons in it. So that's 2 electrons taken care of here. Next, we fill the 2s level. Again, the s's always have 2 electrons, so that's 4 electrons. We go on, as we follow that chart along, to the p, so 2p, which can hold up to 6. We're only up to 10. We haven't gotten up to the 18 electrons yet that we need. The next thing on that chart is the 3s level. Again, the s's will only hold 2, so we're up to 12. And then finally, if we do the 3p6, and we add these up, we've got 6 plus 2 plus 6, that's 12, 14, 15, 16, 17, 18 electrons, and that would be the complete electron configuration for argon. So we've just filled that, we just go along that chart, follow along that little snaking line and fill in, and just remember, as I'll put off to the side here, that the S always has 2 electrons, the P will always have 6 electrons, the D will always have 10 electrons. F will have 14 electrons. So for any element that we'd look at, you'd fill them that way, and as you do the S's, you put 2 electrons in, and you just try to get to that total number of electrons. So let's look at B here. B is actually zinc. Now again, start off. We've got to figure out how many electrons zinc has, and zinc has 30 electrons. So we've got to go a little bit further with this one. So we're going to start off, we know we're going to have to fill the first 18 just like this, because that's the order in which they fill. So 1s2, 2s2, 2p6, 3s2, 3p6. Okay, now we're next. What is next after that? Then we fill the 4s level. So the 4s gets 2, and that'll get us up to 20. And if you notice, this is going to be the first time we're going to fill the D. The D is actually the 3D will come after the 4s. So this will be 3D, and recall the Ds will hold 10 electrons. And that now gives us the 18 we had, plus 2 more for 20, and 10 more makes 30, and we have got the complete electron configuration for zinc. Now, finally, let's do one more of these, and that would be bromine. Again, we'll have to look up how many electrons that has, go to your periodic table, and we'll find that it has 35 electrons. 35 electrons means now we've got to do, there's 30, and we just need 5 more. So we're going to copy the entire thing we just did for zinc. Through the 3D10 level, and now we need 5 more electrons. Well, the next thing that we'll fill is the 4p level. Now 4p will hold 6 electrons. However, we only need 5 of them, so it would be 4p5 is what we need to actually complete this. So that would give us 35 electrons, which is exactly how many bromine should have. So you use that kind of zigzagging table to be able to get the electron configurations. It tells you in which order the electron shells will fill, and then you just have to remember the S's, the P's, the D's, and the F's, and how many electrons go in each shell, and just look for the counts to be correct. Now, as we come to the last couple here, this one asks us to identify how many protons, neutrons, and electrons are in the following isotopes. So we want to count, and if we remember what the numbers tell us when we have something like this, and I'll write one over here, 12 carbon 6, this tells us the atomic number, which is the number of protons. This gives us the atomic mass, which is the sum of the number of protons and the number of neutrons. So the number of protons will always be given there. So let's just do all of these really easy. The protons are 6. Protons are 1, because that's 1. Protons are 18. Protons are again 1. Protons 79. And protons 92. Again, that number tells you directly what the number of protons will be. Now, for the neutrons, we have to subtract. You have to take the atomic mass that's given up here and subtract the number of protons to get to the number of neutrons. So in this case, neutrons is going to be 12 minus 6, which is 6. In this case, the number of neutrons is going to be 1 minus 1, which is 0. The hydrogen atom, regular hydrogen atom, has no neutrons. For argon here, we're going to take 40 minus 18, subtract those two, and get 22. For deuterium, heavier hydrogen, we take the 2 atomic mass minus the 1 and find out that that has 1 neutron. That's how it differs from ordinary hydrogen. Getting up to a little bit heavier elements here, we're going to see the number of neutrons increasing drastically. For gold, we have 197 minus 179, and that would give us 118 neutrons. And finally, for uranium, 235 for the atomic mass minus 92 would leave us with 143 neutrons. Now, electrons, the last thing to figure out here, are also quite easy, because the electrons are going, unless these have a charge associated with them, the number of electrons is always going to match the number of protons. So if it's a neutral atom, which the atoms will always be unless they are otherwise noted with a plus or a minus up above them to the right, then the number of electrons is just equal to the number of protons, or 6 in this case, 1 here, 18, again 1. Here for gold, it's 79, and finally for uranium, it's 92. So in this case, the electrons are very easy, as they're going to have exactly the same number as the number of protons. Finally, the last sample one here is that we're looking at the electron dot notation. We want to look at that for these 6 elements that are given. The electron dot notation is given in your textbook as to how we write that, but let's do a few examples here. In this case, when we do the electron dot notation as compared to the regular electron configuration, we're only looking at the outer shell. We're only looking at the outer 8 electrons. So you start by writing the symbol for the element, and for boron, that would be a B, and then we have to figure out how many electrons boron has. Well, boron has 3 electrons, so if it has 3 electrons, then we have to fill in with our dots. You always put 2 dots. First we fill the S shell, which is to the right, so we put 2 dots there. And then we start going around to fill the rest. And in this case, we only need 1 more, so we start out here up at the top. And that would give us 3 electrons, and that would be the electron configuration for boron. Now, if we look at bromine, the next one, how many electrons does bromine have in its outer shell? Well, bromine would have 7. So 7 electrons in its outer shell means we've got to fill a little bit more. We need to fill that S shell, and now we need still 5 more electrons. And we start at the top and just work our way around. So 1, 2, 3, and then we go back and fill them in, 4 and 5. So this would be the electron configuration for bromine. It would have 1 open slot for another electron. Let's go to calcium. Calcium has 2 electrons. So we only fill the S shell. All calcium is going to have is 2 electrons there, and it's done. Potassium, symbol K, will have only 1 electron. So it doesn't even fill its S shell. It has 1 electron in its outermost shell. So it just gets 1 dot here. So potassium and bromine would want to combine together because bromine needs 1 electron and potassium has 1. Combining together, as we'll see in the coming chapters, gives them both a stable outer shell. Now our last 2 here, let's look at oxygen and sulfur. And oxygen and sulfur are right below each other, and they both have 6 electrons in their outermost shell. So they're going to have exactly the same electron configuration in their outer shell, and therefore the same dot notation, and that means they'll have very similar chemical properties. Let's do their dots here. We do 2 for the S shell, and then we need 4 more. 1, 2, 3, and back up for 4. Sulfur will be exactly the same. 2 here, then 1, 2, 3, and 4. So that would give us the electron dot notation. We'll be able to use that in the next chapter to look at some of the chemical reactions. So that concludes our sample problems for Chapter 8 on periodic properties. We'll be back again next time for the next video. So until then, have a great day, everyone, and I will see you in class.